Excellent. Well, good afternoon, everybody, and welcome to reInvent. Everyone having a good time so far? Enjoying the keynotes this morning? Some cool things? Excellent. Well, welcome to Best Practices for Serverless Developers. But you know what? Actually forgets the serverless part. This is actually for all developers, building in the cloud. A serverless is really the default way to get the most out of the cloud when building applications. My name's Julian. I'm a developer advocate here for serverless, specializing in serverless at AWS. We've got lovely people in the room. We've got some overflow rooms in other parts of Las Vegas at other hotels, so hello to you all virtually. And if you're watching this from the YouTube recording, which will be posted shortly, I suppose hello into the future. So thank you, everybody, for joining me. Today, I'm going to take you through a story that actually mirrors the serverless evolution of, thousands of companies. And in this talk, we're going to follow Amelie's transformation from a single patisserie to international success. And I promise you, there's nothing that I like more than a delicious pastry. It's absolutely my weakness, and I'm just thinking I should have actually brought one now. So the serverless best practices I'm going to teach you is going to help to enable this incredible growth and understand the real-world scaling challenges that every developer is going to face. And you can see the evolution from just getting something out there to a mature serverless architecture. You can see here 5 years of growth, both business growth and architectural growth, and evolution. Each phase brought new challenges, and also there were obviously lessons. Notice the dramatic scaling from 40 orders to 320,000 orders per month, a huge scale. And the architecture had to support this growth, and we're going to see how serverless patterns helped this transformation. So things started, Amelie opened during lockdown following her absolute baking passion. A single Lambda function handled everything, just 200 lines of code, basic DynamoDB table for object storage, for database storage, for orders, and then manual payment processing via phone calls, 40 orders per month from local neighborhood customers. A great sort of minimal viable architecture with basic Lambda functions. Great way to get started. Obviously, the pay-per-use model is perfect for uncertain demand, and zero infrastructure management during a crisis was perfect as well. 2021, the simple architecture still holds, with some splitting of Lambda functions for payment and inventory tracking, a good idea. And then, the first scaling challenges start to emerge. Lambda timeouts during the morning rush, so a performance degradation during peak hours, and something that's always hard to troubleshoot, and team coordination issues too. 2022, more locations, many more orders. Now, 42 Lambda functions, complex dependency chains, and not enough error handling. The morning rush, cascading failures, spiking customer complaints. Performance suffering, 6+ seconds order processing. That's crazy. 3% failure rate during peak hours. Oh no. A breaking point that forces architectural transformation. And so, and with customers getting frustrated with the slow service. And then 2024 was the year to get down and fix things. A proper serverless gradual architecture sort out, bringing in step functions for orchestration, Event Bridge for events, SQS for reliable processing, and reducing 42 Lambda functions down to just 10. 6 seconds down to 400 milliseconds processing time, and a foundation set for some cool international expansion. And it all made a difference for global expansion. 60 locations across Europe and North America, 3.8 million orders per year with great performance and reliability. Handling 40 times the holiday traffic spike seamlessly, and a 35% cost reduction despite 3 times the growth. Amelie's passion project goes to international success. And so we're going to follow Amelie's transformation through a number of different areas, show the problem, some solutions, and some of the lessons learned. And I'm going to give you actionable insights that you can apply to your own serverless applications. Now, I'm going to warn you there's going to be a lot here. I'm going to go both broad and deep, so there's going to be a huge amount of info. And I've included this QR code, which is a link to a handy resources page with the slides from the presentation and plenty of other reference links. And I'm going to do the QR code at the end, so if you miss it, don't worry. And also, if you are watching this on the recording, this is probably not one of those talks that you want to watch at double speed. Maybe half speed is going to be a little easier, but I'll leave that up to you. A lot we're going to cover. So let's start with the foundations, how to size and organize your serverless applications. By 2023, what started as simple order processing had become a monolithic nightmare. A single Lambda function handling orders, validation, notifications, analytics, and a whole bunch of more stuff. Deployment time stretching to 5 minutes. Debugging is, I suppose, like finding a croissant in a bakery full of pastries. And then a holiday rush incident. A single bug in the notification service brought down all the order processing. That is bad. And this crisis forced them to learn proper Lambda sizing principles. And there's some universal principles that do apply. Each Lambda function should generally have one clear responsibility, avoiding a complex do-it-all Lambda functions. And what you want to do is actually size it for what it needs to do, not just for your convenience. Partly, we'll get to that. But Lambda allocates also CPU memory proportionally to memory configuration, and so adding more memory improves performance and also may reduce costs. Package size also directly impacts cold start times, so you do want to make sure your function's small and nimble for your performance. But you can also easily swing the pendulum to the opposite extremes with too many functions or repos or stacks or things to manage. Resist the temptation to create these sort of micro-functions prematurely. Start with cohesive functions and split only when you experience real pain. The 42-function chaos was organic growth really gone probably a bit wrong. And same for also stacks and repos. The goal is a pragmatic approach for your organizational and for your current needs, not your sort of future theoretical perfection. And this is actually probably more an architectural and an organization decision rather than just lines of code. And when you do create clear boundaries, each team can choose a runtime and tooling based on their expertise and needs. And this is unique pretty much to serverless, that you can pick and choose the different kind of things you want to do. Maybe the orders team is going to prefer using SAM or Java. The inventory team uses Python for maybe some great data-heavy workloads. And the customer experience team wants to use TypeScript because they want to use it for both the front end and the back end. And so your infrastructure choices can align with your team's strengths. And this extends also to domain-driven organization, where each domain can also own its own data and own its own functionality and be right-sized for the team, right-sized for what a team can effectively manage by itself. And if you're thinking and you're building serverless apps, just use a framework. It doesn't actually really matter which one. Pick the one that works for you. There are many third-party ones, or we've got SAM, which is an extension of CloudFormation with some simplified syntax, or CDK to create CloudFormation in programming languages. Just use a framework. It's just going to make your life so much easier. Many people also overcomplicate repos too. Please don't have a repo for each function. I beg you, please. That's going to be a nightmare. And you can easily have a single repo for many services with separation between some domain-specific and also some shared infrastructure. The decision on size for actual repos is also all about manageability. So Amelie's transformation was thinking about sizing, making a function smaller, reducing the cold starts, deployment times, and also test runs. 40% lower compute costs through right sizing. Right sizing is the key. And the key principle being, keep it big until it hurts. Right sizing for workloads, organized by business domain, and you can enable team autonomy in your technological choices. So next up, Amelie learned that too much sync and not enough async was killing performance during the morning rush, from sort of blocking chains to event-driven flow. 2023, synchronous architecture starting to create some nightmares during peak hours. The morning rush brought cascading system failures and, of course, frustrated customers. The synchronous chain meant one slow payment API call, for example, blocked everything downstream. Business impact, not good. 23% of orders abandoned, a huge increase in complaints, a revenue loss during the highest traffic periods. And this crisis forced them to understand that the fundamental problems with synchronous architectures. The sequential wait train, if you look through the mermaid diagram here, means every step must finish before you get a response. Everything had to complete in Lambda functions before the customer got a confirmation. And so one slow service affected the entire workflow. And it's all waiting, waiting, and waiting. Long chains can also approach API gateway and even Lambda's timeout limits. And customers abandon orders while waiting for confirmation. And this can manifest itself in two ways. You can have one big Lambda function doing absolutely everything, and it becomes brittle and tough to manage, and also you paying for the waiting time within a Lambda function. Or actually, I think probably even worse is multiple Lambda functions in series, each one a fragile cascading chain. If the third-party payment service has a failure, for example, the rest just stops. A poor user experience and tough to come back from. So Amelie and her team did their research and realized an event-driven design would help, using an event bus for service-to-service calls, stopping direct service dependencies, which allowed for loose coupling, some independent scaling, and means failures in one system don't break the others. And you can still use async callbacks to update the original caller when the work does complete. Which means bringing in some other of our serverless friends like step functions, EventBridge, SQS, and even AppSync events, which is great for the front-end notifications, actually. And what's the mantra for serverless? You want to use the best service for the job. And so the customer gets an immediate order confirmation instead of waiting for absolutely everything. And then EventBridge decouples all the services. Each service processes asynchronously and publishes its own events while done. And AppSync events provides real-time updates back to the client as work completes, and so the customer is going to see the various progresses, payment confirmed, kitchen preparing, and ready for pickups. And you get the best of both worlds. You get that immediate response back to your client, plus real-time progress updates. You get resilience. The payment delays don't affect inventory or notifications. Scalability. Each service can scale independently based on demand. And their clear event trail shows exactly where issues are occurring. And another thing to bring in for asynchronous processing is Lambda's event source mapping. One of the best use cases for Lambda, async processing from a number of event sources with direct Lambda integrations. And event source mapping is a resource that gets events from a source and ultimately sends the event to Lambda for processing. The Lambda service polls event sources automatically. There's some content-based filtering, which can reduce invocations for events you don't need to process. The ESM can batch or group records together for efficient processing, and then ultimately invoke the Lambda function with the batched records. And there's actually an architectural difference between two types of event sources, queues and streams. And queues is great for task processing when each message is independent and messages are deleted after the processing. Streams is more event processing when perhaps you need multiple consumers who need the same data or order matters, and messages are retained for replay. And so a key decision you may have is, do you have one consumer doing work once? Maybe you're going to use a queue, or you've got multiple consumers or need some sort of replay, then you're going to think about doing a stream. And the Lambda ESM provides a bunch of functionality across all of these event sources. You've got the filtering, which I mentioned, batch controls, including for streams, being able to split a batch to find a faulty record, and then choosing where to start in a stream, from the beginning, from the latest stream, or at a particular timestamp. There's some retry and failure handling options built in, some analytics for kinesis, and platform performance configuration options. So a whole bunch. It's just called an ESM, but all of this functionality that is built in. Sorry, there's the performance configuration options. And so Amelie needed a message buffer during traffic spikes to prevent system overload. And so SQS provides perfect decoupling between producers and consumers. Lambda ESM automatically polls SQS and then scales based on the queue depth, and messages are then going to be consumed once and then deleted after a successful processing. And SQS just automatically handles the complexity of any of the message durability and delivery. SQS is an incredible service. And there's a new mode joining Kafka for SQS called provisioned mode. And this allows you to provision event pollers in advance to handle sudden spikes in traffic, which and you've got controls to be able to optimize the throughput. And there is an additional charge based on what's called an event processing unit. Amelie doesn't actually need provision mode, but this can be super useful for high throughput, low latency queue polling. So let's look at some of the best practices for SQS queue configuration. You want to set the visibility timeout, I nearly said invisibility timeout, the visibility timeout to at least 6 times the Lambda function, so messages are available during processing during retries. I suggest also setting the redrive policy for the SQS queue to 3 or probably 5 to also give more chances for successful delivery. And then for message retention, make sure it's long enough to handle any possible break in the system. This is not just in your ESM, but maybe in your whole company or maybe in a whole region, so messages aren't lost during some downtime. And then you must set a DL queue, which is a dead letter queue, so any messages that Lambda can't process are sent to this other queue and then are not lost. And then you want also some process to be able to recover these messages from the DL queue and be able to replay them into the main SQS queue. And from the Lambda ESM side, you want to also ensure that you can process messages and also protect downstream sources from a surge. That is the point of having a queue. For processing messages, the Lambda on-demand ESM can scale up to 1,250 concurrent invokes per event source, and then use provision mode, as I said, if you want faster scaling, and also up to 16 times higher concurrency. 16 times higher concurrency, that's 20,000. And that's some impressive throughput, which you can use for your SQS queues with Lambda. Filtering also allows you to only process the messages you need. And you can use positive filtering to pick which messages you do want to process, also negative filtering for a flexible query to say which messages you don't want to process. And this is a very powerful thing, saves you money, saves you time, and it also uses the event bridge syntax for filtering, so it's also consistency. And also mentions, obviously, this can save you a bunch of money. And using this, Amelie was actually able to reduce costs for one of their ESMs for 92% by just using filtering. Batch sizes, I recommend just tend to get started. You may as well start with that. It does mean fewer invokes and still decent throughput, because the larger the batch size, the fewer invokes, and so that's one thing you need to think about. See how you go, but batch sizes can go up to 10,000, which is a huge batch size, and that can be super useful in some of your scenarios. The batch window here is then to improve the latency when you actually don't have much traffic. So you get to process messages before a batch number is formed. So you can use these two different settings for different use cases. And then also you've got the partial batch, the report batch item failures. So if you do have a faulty record in your processing, you return a list of failed records back to SQS, and SQS is then going to delete the process messages, which is more efficient rather than having to retry an entire batch. So then to control the flow control, this is the rate at which Lambda consumes the messages, you want to set the max concurrency on the ESM. And this is going to control how many concurrent invocations the ESM attempts to send to Lambda, which prevents overwhelming downstream services. These could be things like databases or APIs or any third-party services which can only handle a certain amount of throughput. And this is actually the all-important buffering control system. And then Lambda reserve concurrency is a separate setting which you can set at the Lambda function level, and this actually reserves capacity for this function, ensuring it can scale up when needed within the account concurrency. And so you want to rather use max concurrency to manage the buffer, but if you do want to use both together, make sure that your reserve concurrency is higher than the max concurrency to prevent throttling. So do two different settings for two different things, and you can use them together. And then the last bit is for more error handling. So this is configuring Lambda on failure destinations for function invoke issues. And then you may be thinking, so why are there actually two different error handling parts? Well, the SQS DLQ captures messages that fail repeatedly during polling or processing, and that is on the SQS side, while Lambda on failure destinations captures invocation failures like network issues, throttling, or maybe even if you deleted a function or you've got some kind of IAM issue. And so both serve different processes and should be used together for comprehensive error handling. So moving to async is a powerful architecture that actually should really be your default choice, in my opinion, avoiding synchronous chains that can go wrong. You want to store first, you want to reply quickly for better user experience, and then process things later. And this is a very powerful, resilient, and stable model. Understanding also when to use queues versus streams. And async also means better failure isolation, but you then do need to think about retries and not losing any messages. So next, Amelie learned how to avoid unnecessary work through using step functions, orchestration, and some direct service integrations. 2024, Amelie had successfully moved over to async architecture, but created a new problem. 42 Lambda functions, as we said before, including many doing just simple data transformations and routing. That means high compute costs for operations that didn't require any sort of custom business logic, cold starts affecting performance for basically CRUD database updates, and complex failure scenarios across multiple function invocations. And this led to the discovery that configuration as code could replace many Lambda functions. You basically want to avoid Lambda when you need to use native capabilities in other services. Less code to manage. I don't know about your code, my code, I want less code of that to manage. Your code is probably great, so you may be good with that. But for things like simple data transformations, direct service-to-service calls, only routing data from one place to another, or simple data enrichment, you don't need to use Lambda. If you do have Lambda functions that serve only as a proxy, for example, I'm going to go through some direct integrations between API gateway and downstream service, you can optimize that. So you can see on the right, API gateway can actually connect directly to multiple AWS services, such as Dynamo, SQS, step functions, and many more. Once again, no need to use Lambda just as a proxy. And I understand that VTL is a bit of a pain to test, but also once you do have it configured, it's done forever. And for a simple example like this DynamoDB get item request, it's easy, cheap, and it's fast. And more great opportunities to remove code. One common pattern that a lot of customers use is using Lambda to capture DynamoDB change events or change data capture events from a lot of other services if they support it. Lambda then passes the events and then sends them to another service, an event bus or API for some other downstream processing. Event bridge pipes, well, this provides built-in transformation capabilities. JSON path provides a powerful data manipulation and filtering only needed events. You can enrich data as part of the pipe, do data format conversions, transformations. You can also use step functions, and you can also use Lambda as part of this the step as well. And then it's going to batch it up for efficient downstream processing. And this is perfect for simple data transformations that don't necessarily require complex business logic. This is it just if you're using the pipe by itself without step functions and event bridge. But yeah, this is, reduces your Lambda invocations for basic event processing, and it's really simple to set up. But actually, the big winner in Amelie's use case is using step functions, being able to remove a bunch of Lambda functions for direct service calls. You can see all of the AWS SDK actions are available, so in effect, there are thousands and thousands of integrations. And here's the config to update inventory in Dynamo. Just a simple configuration call that you put in a step functions state, and it's really easy to call, and there's a whole bunch of stuff around it with no cold states, no cold starts, and safe retries are also built in. And there's also built-in JSON support with loads of these functions, including some step function-specific ones, like generating a UUID. So this is super useful. You want to count things, you want to do up some numbers, the length, and all these kind of things. No need to have a Lambda function. You can just use pretty much free JSON expressions to be able to do it. So these are very powerful ways to build up a lot of functionality without having to maintain any of your custom code. In many scenarios, step functions is then used in conjunction with Event Bridge. And step functions is great probably within a domain microservice, and then the pattern is to finish what the service needs to do, and that's going to be whether that is step functions, whether it's even a Lambda function, and the pattern is to then emit an event onto the event bus, and this is then going to enable the event-driven communication between different domains. A very powerful model, allows you to add as many domains as you need without being sort of trampling on each other. And if you didn't know, there are actually two different flavors of step functions. There's standard workflows, which can run for up to a year and are asynchronous, and express workflows, which are fast and furious. And these are specifically built for high throughput. And they can run for a maximum of 5 minutes, and they can also be synchronous. So super useful for doing that synchronous calling we were talking about earlier. The pricing is different. Standard workflows are priced per state transition, and express workflows are then priced by the number of executions and memory consumption. And express workflows also run in memory, so they're super fast. And the best part is you can, and actually you should, combine standard and express workflows. You can combine the durability of standard workflows with the speed of express workflows. And so this is perfect for scenarios where most of the process is long running, but some of the parts of your state machine need some real-time responses. And so here we can see the standard workflow is going to run start execution and orchestrate the complete order processing lifecycle with a full order trail as part of the standard workflows. And then it's going to run the start execution and run the nested express workflow to handle real-time inventory validation in some second time. And what it can do in the express workflow, it can do other cool step functions things like running a parallel state to check the inventory and the pricing rules simultaneously. And then it's also using DynamoDB direct service integrations. So again, no Lambda cold starts. All becomes nice and simple. But actually, as announced in the keynote today, there's a new kid on the block for asynchronous processing, but still within a Lambda function. Lambda with durable functions being announced today. And this actually does completely change the way you think about Lambda functions. You can now build workflows in your favorite programming language. You're able to use checkpointing to suspend and resume long-running operations with idempotency just built in. So this is actually useful when you have a bunch of Lambda code in your workflows, and you can now use the enhanced context object like I'm highlighting over here. And I'm showing you can run steps, you can do parallel processing, and even wait for callback all within an async Lambda function within the Lambda function, and you don't pay for that wait time as well, and they can run for up to a year. So if your mind's going a bit, hang on, this is all a bit strange and different for Lambda, I'm with you, but this is a super powerful way, a new capability that we announced today. Step functions, of course, is still great, particularly for those direct service integrations. But if your workflow does require a lot of your own code, or you'd prefer just managing your workflow in code with async checkpointing and resume, this is certainly worth taking a look. And my good friends Michael Gash and Eric Johnson are doing a dedicated talk tomorrow, and that's going to be diving deep into it. I think it may be Mandalay Bay, but I'm not entirely sure. At CNS403, so I have that look that hopefully should be released in the content catalog today. Durable functions is going to be awesome. Well, it is awesome. So going all async helped Amelie being able to drastically reduce Lambda functions and cold starts, improving latency, better timeouts, better error handling due to reliable service integrations, and a monthly saving of $1,500 just from eliminating unnecessary Lambda functions. So this demonstrates the power of configuration as code over custom compute. Remember, the good old adage, the best Lambda function is often the one you don't even have to write. So next up, Amelie optimized Lambda performance for functions that truly needed the custom logic, because Lambda still is a great service when you need to use it. 2023, 35 locations, 180,000 orders monthly. The morning rush created a perfect storm of performance problems. Customers abandoned orders faster than Amelie could even bake croissants, which meant a revenue loss, and that's not good. And this was an existential business threat, not even just a technical problem. And so, quick sidebar for performance and cost, there's also another Lambda kid on the block announced this week, Lambda Managed Instances. And this actually gives you the Lambda operational simplicity and serverless operational model to go with EC2's full ranges and specificity. We manage the hardware, and it runs in your VPC. You can choose specialized instance based on memory or CPU or network, and then Lambda's just going to manage and handling this instance. And there's multi-currency actually built in, another mine thing and another change that Lambda's going to be able to support for this model. But you do need to handle this in your code. There's going to be a lot of information coming out about how to do that. The same timeouts do apply, but this can be a big cost saving for at-scale workloads where you can use also your EC2 pricing plans, so things like reserved instances. So this isn't for everybody. If you're at high scale and you've got really steady state functions, it doesn't spin up as quickly and being able to burst and all that kind of thing, but it at least is an option at high scale if you want to be able to manage your costs when you grow with Lambda. Again, there's another dedicated talk on Thursday from Stephen and Ashana that's going to dive deep into it, and it's worth watching to understand how concurrency changes for this model. And definitely check for this one, and this is in the content catalog. So let's take a look back at the normal Lambda function lifecycle. Lambda creates a new execution environment, or for managed instances, actually it deploys a container onto the EC2 instances. It then downloads your code or your container image, starts the runtime, and then we have to run your function handler pre-initialization code and your first invoke. And then after that point, your function is warm and ready to run the event that's been sent to it. There's actually a separation here between what you can control and what we control. And essentially, everything up to the init of the runtime is AWS's problem. And the Lambda team spends an inordinate amount of time over the years here, literally shaving down to nanoseconds, trying to improve performance and trying to make everything that becomes on our side of the line faster and faster and faster. So the parts that you can control are memory allocation for performance, your initialization code, your function handler code, and then the package size. So Lambda allocates CPU power proportionally to memory configurations up to 10 gig for on-demand functions and up to 30 gig for managed instance functions. Lambda also proportionally allocates CPU power based on memory, and for managed instances, you can actually configure the ratio of memory to virtual CPU that you actually want for your workload. And for on-demand, once you allocated more memory past about 1.8 gig, you can actually use more cores, so multi-threading becomes possible. And it's counterintuitive, but actually higher memory often reduces total cost. If your code is CPU-bound, adding memory improves the performance and may reduce the cost. And the key is to finding the sweet spot where performance gains justify memory costs. So you add more memory, it adds more CPU oomph, and so things can be processed quickly, and that can reduce your costs. Now, for on-demand, if you want to take advantage of more power with more than one CPU, you can use parallel processing within your Lambda function code. So if we say here, are processing a batch of records, doing this sequentially is going to take 300 milliseconds for 3 records. And within your code, when you use the process record in your code, this is going to process each record at a time. But you can actually speed this up using multiple cores and running this in parallel. And so it's only going to take 100 milliseconds for all 3 because you can use promises to run the code in parallel. And this is a super unlock for batch processing to get the most for your CPUs. Now, working out the optimal memory configuration, that can be a manual process. You've got to try all the options to do it all yourself. And so Lambda Power Tuning is an open source tool that gives you a data-driven approach to help you visualize and fine-tune the memory power of your Lambda functions. It runs multiple current executions of your function at all the different memory allocations you pick, and then measures how they perform. And it runs in your accounts, performing your real function calls, showing the real cost and speed, and this helps you to find the right balance in an automated way. Okay, so on to cold starts. Here, Amelie has her figures, and cold starts affect less than 1% of invocations in her production workload. And they primarily occur during scaling up or after function updates. And so you generally want to focus cold start optimization on latency-sensitive, user-facing workloads. Async workloads can usually tolerate some cold start latency, unless you may be using something like provision mode and you need to do a whole bunch of throughput processing. But generally, all those async processes, if it takes a few milliseconds or even a second for a payment notification email to come through, nobody's really going to mind. And so don't over-optimize cold starts for background processing functions. Although, I did mention there's a cost win for doing this, but isn't the biggest thing that you can do for performance. But there is a bunch of stuff that you can do to make your init more efficient. Focus on what you can control, the package size, the imports, and the initialization logic. You only want to import specific models that you need. So you want to avoid importing huge, big SDKs when you're only going to use a small part of it. If you're using Node or TypeScript or that kind of thing, you can minify production code to reduce the download time. Lazy initialization, if you do have functions that do some multiple processes, and so this can defer some heavy operations until they're actually needed for maybe only part of the invokes. You can also think about establishing connections during the init phase and then reusing them during subsequent invocations when we're talking about warm starts. But of course, you do need to think and you need to make sure that you can handle reconnections in your handler to deal with any of those stale connections. Keep alives also maintain persistent connections to other AWS services, and then also you can cache reusable data, but also you need to think about cleaning up sensitive data. If you've got subsequent invokes and you've got information from different customers or things like that, or secrets that pertain to different IAM roles, or all those kind of things, you do need to think about that to make your functions safe. Now, there are also a lot of code optimization strategies. I'm not going to go through all of these, but because each runtime has specific optimization techniques. And really, there's nothing groundbreaking here. These are just often, a lot of them are just normal code best practices. Java can benefit from using snapstart and proper SDK usage. JavaScript or TypeScript can use modular SDKs, and specifically using the version 3 of the AWS SDK, and also things like tree shaking. .NET can leverage AOT compilation for faster startup, and then Python optimization is often all about your import strategy and the package size. But remember, for all of these, connection reuse is critical across all the runtimes to save you time. There are some native compilation options that can provide significant performance benefits. GraalVM compiles Java to native executables with sub-second cold start times. .NET AOT does the similar kind of thing for .NET applications. Now, obviously, there are trade-offs with this approach. There may be some longer build times and some runtime limitations and a different sort of runtime that you maybe need to use. But this is a useful thing that you can look at, and this is often best for CPU-intensive workloads with predictable execution patterns, so you can run these. It does obviously require some code changes and the framework compatibility considerations, but more and more frameworks are supporting them. And so this is most effective for functions that also frequently invoked or also are cold start sensitive. And we also have some platform features like provision concurrency and snapstart to eliminate cold starts without any code changes, and we'll get into that. So provision concurrency is available for all languages. You configure it then for a certain value, and then Lambda effectively goes ahead and pre-warms those execution environments, runs that initialization process in advance, and then we're going to keep those execution environments around for you. As they age out, we're going to replace them automatically. And so here I've turned on provision concurrency for this function for version 10. You can see the inits are running in advance, and then when the invokes come in, they land on those already warmed execution environments. And so you won't see a cold start in front of these environments, and so this is helpful just before that sort of 8 p.m. patisserie rush from the morning rush that Amelie would need it. Two other things: don't actually pay for provision concurrency you don't use. There's a cloud metric to monitor this, so don't waste any of your money. And I pushed over too fast. And then also, you must use the function version alias, not $latest. That trips people out when they wonder, why is my provision concurrency not doing anything? So when to use it? This is for applications that need less than 100 milliseconds of startup latency. So you need to configure the value for provision concurrency, so it's best for predictable traffic patterns, which justify the cost of keeping those warm environments up and running. So obviously, it's going to be good for mission-critical APIs where any latency variable is unacceptable, or some high-traffic applications needing consistent performance during heavy periods. Now, for implementation, I suggest you sort of need to do some research and understand your execution patterns. What times of the day do you need to pre-provision the provision concurrency? And you can just start with a static figure and then maybe evolve it into something dynamic, configuring it using application autoscaling for just when you need it. And that can be very efficient to be able to ramp up beforehand and ramp down afterwards. And with Lambda's new, more recent, I suppose a year ago now, scalability things, it's really quick to get provision concurrency up and running in advance. So then Lambda Snapstart for Java, Python, or .NET is another platform feature that runs the cold start process when you publish a function in advance, so not actually just before an invoke. And so when you need to invoke the function, it's going to resume the snapshot, and it's generally going to do this in under a second, and so it makes it perfect for cost-sensitive applications with unpredictable traffic. There's no additional cost, which makes it a great workloads where provision concurrency would be expensive. Functions with heavy runtime startup or loading heavy dependencies, they're going to be the ones that see the biggest benefit. Java is going to see great performance gains to having to start up the JVM. Python is going to benefit significantly when loading big ML frameworks, and .NET gains from eliminating the JIT compilation delays. And remember again to target a function version, and you also cannot use both snapshot and provision concurrency at the same time. So what can you do to actually make that snapshot process as efficient as possible? For Java, what you can use the before checkpoint hook to preload dependencies and initialize resources using the init phase. And this actually uses the crack runtime hooks, which is from an open source project. And there are two ways to do this. You can actually use invoke priming, which does have the highest performance, but make sure that you then use stub data and your code must be idempotent as you're actually running real live invokes for your Lambda function to set this up. Or you can choose to use class priming, and this is then going to load classes without actually the method of execution. So two different ways, but you want to run as much as you can in this init process, so that's going to optimize your invokes. And for .NET, it's actually want to run multiple invokes as part of the init using the register before snapshot, which is what makes .NET snapshot really effective. And literally, you want to run probably maybe even 10 or 20 times, and this signals the .NET runtime to perform tiered compilation aggressively. It's sort of, I suppose, think of saying to the runtime, this code is hot, optimize it as aggressively as you can. And again, use dummy or stub data to avoid side effects during warm-up because you are running real invokes. And this works with many frameworks as well. So there's some universal best practices for snap start. You want to reestablish network connections after restore. State isn't going to be guaranteed. You want to generate unique IDs and secrets after the initialization. And then you obviously want to refresh credentials and timestamps then in your handler. And of course, only executed init code paths are captured, so you want to use those runtime hooks we spoke about to warm those critical paths. And then again, you must use function versions, not $latest, and obviously you want to test with your realistic workloads. And CloudWatch metrics can be your friend to validate the performance improvement with your business impact. Snapshot is actually a really great, quick and easy win to be able to improve cold start performance. Another optimization tip, just upgrade your runtime. Seriously, it's often one of the simplest things to do. In this example, upgrading Python had a dramatic increase in latency, which improves performance and reduces cost. Languages are continually evolving, and help keeping up to date with runtimes means you also get the best performance for your buck. And of course, there's a security implication for this as well. So a systematic approach delivered dramatic improvements, starting with memory right-sizing, the main kind of thing, the biggest impact, the easiest implementation. Code optimization provided additional gains through better resource utilization. Cold start mitigation ensured consistent performance during traffic spikes. And native compilation provided that last little performance boost for CPU-intensive workloads. So next up, how Emily built resilient systems through proper failure handling and error recovery. Lots of locations, 35 of them processing thousands of orders daily. That holiday rush I spoke about earlier created this sort of perfect storm of cascading failures, payment issues, a crashed order system, no notifications, manual recovery. Obviously, this is a big business impact. Lost revenue, angry customers, a confused kitchen, what's going on? So of course, this crisis forced them to understand that resilience is also a business imperative. So with all of this, the most important thing to think about is idempotency. Idempotency ensures operations have the same effect whether executed once or multiple times. And this is critical for distributed systems where retries, duplicates, and out-of-order processing occur. Basically, I don't want to be charged twice, so please build all your idempotency operations. But you do then need to think about your idempotency, what that idempotency key is, that sort of unique transaction identifier. Is it going to be an order ID or something that you can use for your idempotency? And many AWS services provide built-in idempotency, which you may not know about. DynamoDB, you can use conditional writes, and so this is going to prevent duplicate operations. SQS FIFO queues can use a message duplication ID for automatic deduplication. And did you actually know for step functions, you can just specify an execution name to prevent duplicates. So you've got a step functions workflow, just provide the name. If the same name has happened before, and you can use that, maybe an order ID or that kind of thing, step functions won't run it. So simple, and a lot of people don't know. And of course, Lambda durable functions is another way because idempotency is just part of the checkpointing part of it. And for your code, Power Tools for AWS Lambda, this is a tool and library for .NET, for Python, for Java, and for Node and TypeScript. Just use this for your functions. It has a huge amount of functionality. Idempotency is included, and it actually just uses DynamoDB behind the scenes. You just set it up in your code, and idempotency is handled for you. Super useful. So we already covered SQS's deal queues and Lambda destinations. This is all part of your failure handling toolkit. And remember, retries are all built into step functions. When you're using step functions, set as configuration, part of your failure and error handling. And you have retry, you've got a catch states, you've got choice and parallel states, and this can give you a whole lot of error handling goodness. If you're building saga patterns or other kind of things, a whole bunch of functionality. And so Amelie's order processing workflow has comprehensive error handling at each step to preventing single failures from bringing down the entire order process. And if you prefer the full code approach, we've got new options now with Lambda durable functions. So next, Amelie gained complete visibility into their serverless systems through advanced observability. 35 locations, system visibility gaps across services, difficult to trace orders, going to identify bottlenecks causing the slow processing, where they're coming from, or trying to connect actually some of the technical metrics also to the business impact. And the breaking point was an undetected payment issue which happened for 2 hours, resulted in hundreds of lost orders and $12,000 in revenue loss during the dinner rush. Now, that's not a good thing that any fledgling business wants to run. No one wants to fly blind. Now, observability is a massive topic, and it's in a fast-moving place, and there are many breakouts here at reInvent, which is all about observability. So I'm just going to give you some of the new things that you can explore to find out to help you out. I love Charity Majors' work. She works for Honeycomb, and she talks a lot more about more than just the pillars of observability, but a bunch of different signals of data which you can use for unified observability data. And seriously, read up Charity Majors, read everything she writes about and talks about observability. She's an absolute guru and amazing. So you've got things like metrics and logs and traces and events and profiling, and they can all be part of these signals, and other kind of business things that can come in. Observability is a big thing. But the thing I want you to take away is you want to really focus on embedding business context in all of the signals for rapid troubleshooting. So this isn't just a technical monitoring thing, this is observability, and the business is very much part of it. So this shifts your thinking from not sort of only monitoring failures to being able to answer questions about individual things to understand your business. Again, Power Tools is your friend here for observability. It just makes things so much easier. You can import the libraries really quickly, configure up your service names, and then it's easy to set up the logging and the metrics as well. And this is then going to use structured logging behind the scenes and using the embedded metrics format to create metrics from the logs entries automatically. A single log write creates both searchable logs and CloudWatch metrics, and this is also faster and cheaper. This is a great way then to incorporate that business context I was talking about, like an order ID for the logs, without having it as a metric dimension, which is going to be pricey. So here we see both entries written to CloudWatch logs in a single log stream. The regular logs are queryable with CloudWatch Insights for debugging, and then the EMF entry lets CloudWatch automatically extract the metrics from it, a powerful 2-for-1. CloudWatch Metrics also has a bunch of new stuff like powerful tag-based automation with filtering on alarming instead of configuring individual function alarm tags, and this makes it way easier. And it's cheaper. You've got one alarm instead of 50, and individual alarms reduce the CloudWatch costs. There's really fancy querying capabilities now available, and a cool new dynamic dashboard where you can actually build up your dashboard, and then you can just select your environment with a drop-down selection, and it changes all in real time. The query generator converts natural language to CloudWatch metrics SQL and allows you to refine existing queries, which I found so much easier. The metrics history has also been extended from 3 hours all the way up to 2 weeks for historical analysis. CloudWatch Application Signals is also something to look at, a new observability solution which is based on open telemetry, and this can also automatically discover services, and it's got a more advanced service map and a whole bunch of other things. So I can't do CloudWatch justice here, and I don't want to flick over kind of things. So the awesome Joe Eliotto has done a great video on all the new things, and there are going to be new things announced this week as well. So I just really suggest you taking as a look, because there's a huge amount going on that's gone on in observability this year, which can really help with your business. So talking about OTel for Lambda. Well, the X-Ray SDK is coming to an end. X-Ray as a service continues, but it's moving to OTel for instrumentation using the AWS distro for OpenTelemetry. If you want to start looking at this for Lambda, there is an ADOT layer, but we actually recommend using the application signals Lambda layer. It's actually an advanced, enhanced version of ADOT, specifically optimized for Lambda, with better performance and lower resource consumption. You can also configure the application signals to use only the OTel libraries for instrumentation without all the other features for application signals by just setting an environment variable. So moving to OTel at the moment does mean a little bit more money and a small cold start penalty, but if OTel is your thing, at least we've got some good options. And of course, we love partnering with others, so you can use your favorite third-party tools with Lambda to get the observability you need. And so Amelie did a lot of observability work, more than I can cover here in the time, but it all pays off. A transformation from disaster-prone to highly reliable system. Better reliability, recovery times, less tail chasing. Black Friday 2024 had 0 outages during a peak traffic and far less customer complaints to better error handling. Next, let's talk about costs and how Amelie optimized costs using design while scaling. Patisserie Amelie started the serverless journey with excitement, but faced unexpected cost challenges. This can happen to you. Monthly AWS bills jumping from $200 to $2,000 without much warning. During a growth phase, Lambda invocations spiking crazily, maybe over-provisioned Lambda functions with too much memory, CloudWatch logs accumulating gigabytes of data daily, each new restaurant adding more and more infrastructure costs, and data transfer and storage costs all adding up. And Amelie realized that in serverless, architecture decisions rarely impact costs. Understanding serverless pricing is crucial for cost-effective architectural decisions. Lambda is on demand. It uses pay-per-use model with charges for requests and then also your compute time. So the init time is charged from this year to remember, and this was to avoid complexity with some inits charging and not some inits not being charged. So it's all across the board, inits are charged. And then per millisecond billing is super powerful with each invoke, and of course those inits charged separately. And so this is cost-effective when there are gaps in work to do. And you can also consider Lambda managed instances for bigger steady-state workloads where you can run Lambda at scale in a cost-effective manner. Now, Fargate uses time-based model with charges for CPU and memory per hour. You pay for what you provision. Now, I didn't have enough time today. There was enough to talk about to go into all Fargate best practices, but it is a super great solution for many workloads when you don't want to use an event-driven model. And it can also be cheaper than Lambda at scale. Continuous processing or long-running predictive workloads are going to favor Fargate, and sporadic event-driven processing is going to favor Lambda. Even though Lambda can scale up to super high workloads, this is cost things that you can work out. For step functions, express workflows can also be significantly cheaper. Amelie is using both, but you can see how pricing can be cheaper. Many more invocations for 1/20th of the cost in this example using express workflows. So also take a look at your existing state machines and see whether you can potentially save some money and then consider using express workflows first when you're building your next applications. And optimizing your logging costs can be an easy win. AWS rolled out tiered pricing for logs this year. Basically, the more you log, the cheaper it gets per gigabyte. The best part, it's automatic. You don't have to do anything. It's just going to be cheaper. Use structured logging with smart log levels. Maybe you're going to set info as your default. Maybe you're going to sample debug logs sparingly and use Lambda Power tools for efficient logging without the custom code overhead. You also want to match your retention to reality. Maybe you need 30 days for dev, 90 for staging, 3 to 6 months for production. I don't know, it's going to depend on your workload, but basically don't stop paying for logs you're never going to use. Also, don't log what you don't need to. Skip massive payloads in your logs, just log key identifiers instead. You can also archive to S3 now for long-term storage, or log directly to Data Firehose when you want high throughput and maybe want to send the logs to some other destinations. And lastly, monitor those costs. You want to set CloudWatch billing alerts and use Cost Explorer to identify your biggest log spenders. So there's lots that Amelie did which reduce costs, which also we covered in some other kind of sections. Right-sizing was the biggest flex to not pay unnecessarily. Filtering is obvious to not just have to work on things that you don't need to, but it's going to be able to avoid a whole bunch of cost unnecessarily. And also using compute savings plans. Amelie is looking to explore that as well. She hasn't quite done that, but that's another kind of option. And so with some simple optimizations, you can make a big difference on costs. Every architecture decision has a direct cost impact. Understand your pricing models, monitor your usage patterns, and then optimize based on your actual requirements. So next up, integrating AI capabilities into their serverless architectures. This is the year of 2025. I don't think anybody at any conference in IT in the world is unable to talk about Gen AI, but it is an important and I think an interesting part that we can look at. By this year, Amelie's 60 global locations faced challenges traditional automation just couldn't solve. If you've got 12,000 monthly inquiries, that's going to overwhelm your support team, if you need to particularly handle multiple languages. 4.3 million orders with minimal personalization. Maybe you can do some more with that, so you're missing some revenue opportunities, and manual decision-making for pricing and inventory. Amelie starts to look at this, to AI to help with this, and maybe take their business to the next level. But Amelie also knows that AI is a journey to also work out what's real and what's hype. And I know we're all probably struggling here at the moment trying to work out what the best use cases in your business. And of course, all of AI could be a whole nother session, but I'm pretty sure here at reInvent this year, there are going to be a few other Gen AI sessions to help with whatever Gen AI things you're going to be looking at. So first thing they realized in the investigations is that Gen AI is just another workload. The same rules apply. What do you need to do? You need to protect endpoints, you need to think about quotas, you need to handle security, you need to think about performance. Everything you know and love about serverless still applies. There's less infrastructure to manage, variable compute demands, pay-per-use are all good. Using async event-driven processing allows AI to respond to business events like orders, inquiries, and inventory changes. Automatic scaling handles traffic spikes without capacity planning, and your existing serverless skills transfer directly. Event-driven architectures, cost optimization, and observability. And Bedrock, as an example, is a serverless service. The pricing is based on input-output tokens, automatic scaling to demand, with enterprise security and compliance built in. And in fact, if you look around the industry, at the Gen AI landscape, most of it is just good old-fashioned serverless. Any kind of model you're using, it's all token-based pricing, all pay-per-use. So yeah, serverless is definitely very applicable in the AI world. And of course, you can integrate Bedrock with all other serverless services. For compute, there are plenty of different options, and step functions is great if you want to do some complex multi-step AI workflows. Event routing and response distribution are needed with EventBridge to help, and DynamoDB and S3 can also be used for storage of many, many things. And then we want to understand the sort of main two parts with AI that are relevant. Agents, the orchestrators, and tools as the executors. Agents run in an orchestrated loop to do something you've basically told it to do. It calls the tools to do the things, then figures out what the next stage is to satisfy your request. And they're often long-running, needing to maintain state, the agents. And so we could decide whether agents are short or long-running and pick the best serverless service to do this, whether that's going to be Lambda or Fargate. But what we actually learned from a decade worth of serverless is rather use a service that is purpose-built for the job. And so Bedrock Agent Core is built for running agents, and it abstracts a lot of the heavy lifting, so you can head up the stack for a managed service the true serverless way. Agent Core's got a bunch of capabilities, a secure managed runtime to run your long-running agents with pay-per-use, and that actually runs a Lambda Firecracker instance for you, all abstracted and behind the scenes. So we're taking the learnings from other serverless services like Lambda and applying them to more things. An MCP gateway to connect to existing APIs and tools, conversation memory, inbound and outbound identity. Agent Core is also framework and protocol agnostic, and the cool thing is it's a bunch of capabilities you don't need to build yourself, and also you don't have to use them all. You can just use one, use two, use all of them, doesn't matter. It's built very specifically that you can pick and choose the useful things that you're going to do. So for identity, for example, sure, you could spin up a DynamoDB instance, store your conversation history and manage that all. You could just use identity, and it's all built in with semantic search as part of the package. And then tools. And these are what the agents call to actually do something. And the tools are actually what you likely already have. Maybe that's something behind an API that reads or writes data from a database, does some action, connects to your private data, something on-prem, something within your own VPC. Actually, the tools are the deterministic part within Gen AI. You know exactly how they work, what functions they can perform, and they're avoiding hallucinations. And in fact, I think you actually want to focus more on the tools side. Even if you don't have robust APIs yet, but with MCP or something like that in front of them, you've actually got more freedom to be able to experiment, as APIs are forever. But because MCP abstracts them, you can have things internal that you can expose externally without having to worry too much about your APIs. You want to worry about your APIs, but having this MCP intermediary layer can be super powerful. And of course, Lambda is great for tools, standalone or behind an API, because they've got fast startup, they can connect to anything, things in your VPC, things anywhere, your data, your VPC, and they are super secure. So just two examples I've got here. What Amelie built, a new customer service AI agent to integrate with existing functionality. The customer inquiry goes into an agent using MCP. Agent Core manages the AI agent runtime with Bedrock while using the gateway to connect to APIs and then to connect to Lambda functions as stateless tools. And so Agent Core is going to handle the orchestration, the state management, and the observability automatically, and the team could then focus on building the actual tools and not having to worry too much about building the agents. Another intelligent recommendation was a good idea they had. This is based on an order-created event which spurs EventBridge into action. Lambda processes context. Bedrock is then going to provide some AI analysis, and DynamoDB is going to store the profiles. Recommendations can adapt during sessions. So this is basically when someone does a payment, it's going to pop up, oh, do you also want to buy this? And so it can use time or weather or location or cross-location insights. Contextual, personalized upselling is really good for customers and also for their business. And so far, Amelie's AI's results are a good start and they are welcome. 70% customer service automation using Agent Core and Lambda tools, 12% revenue growth by using their upselling with what's in your cart, and also a faster development, focusing on the tools and not on the infrastructure, and cost efficiency, pay-per-use for the agents and the tools. And haven't got time as well, but there's not even including the AI coding assistance that the team is taking on. Using Kiro for Spectrum development, which is literally speeding up everything and building really good production-grade applications, and then using the serverless MCP server, which you can connect into Kiro, and in fact, any MCP client, and this really uplists your serverless best practices. You can use natural language, you can query about MCPs, you can query about what infrastructure's code tools, Lambda optimizations, step functions, all these kind of things built into that MCP server. I really suggest you take a look. So, after all that, I said I'd cover a lot, and I did. Let's recap to see what Amelie's journey revealed. Is everybody okay? You're hanging in there? Good. Serverless works at any scale, from 40 orders to 320,000. Serverless architectures had to evolve to support this growth, but serverless, of course, was the best way to achieve this. We had some core principles. Here's the QR code again for the presentation and more handy jumping off links. Right-sizing, matching the function repo and stack size to your workload. Async over sync, EventBridge and queues for resiliency with still faster customer updates. Avoiding work if you can, using direct service integrations, step functions, filtering early, using batch operations. Performance optimization, optimizing those cold starts. Function code optimization. Platform functionality with provision concurrency and snap start. Failure handling. We've got retries, deal queues, circuit breakers, a whole bunch of things. We've got observability, logs, metrics, signals with business context and lots of new CloudWatch goodness. And cost being architecture, every decision has a price tag. And GenAI, just another workload, your serverless skills apply. And these principles also apply at any scale. So what could be your next steps? Well, this week, maybe next week, I think you're going to be broken from reInvent. But pick one Lambda function to optimize. Add some structured logging, including some business context. Implement proper error handling, using retries and deal queues if you're using SQS. Check function sizing, make sure you correctly size your memory. And use EventBridge, not direct invocations. And then once you start there, you can build some momentum. Migrate one sync workload to async, build robust workflows considering step functions or Lambda durable functions, implement some event filtering, save yourself some money, review and optimize those costs, and then also document your patterns to be able to scale out your efforts. There are lots of other sessions going on this week, a Lambda managed instance and durable functions I mentioned in the talk as well. There's also a leadership session, building the future with AWS serverless, and a shameless plug, I'll be back tomorrow with a Lambda principal engineer, and we're going to be talking in detail all about how events travel through Lambda, specifically with polling, and that's going to be back here tomorrow. This link also provides a bunch of additional information to continuous serverless learning. It's got links to power tools, a bunch of the announcements, serverless land patterns, if you've ever used that. That is infrastructure as code and function code examples for all the serverless services, and you just be able to do them, and a whole bunch of them you can use directly in your IDE as well. Super useful. Serverlessland.com as well is the best website to keep up to date with all things serverless on AWS. Lots of cool stuff that you can read over there. But most importantly, thank you for joining me today. I appreciate you taking out the time if you've had to move across Vegas and come to another venue. Thank you so much. I also really appreciate if you could fill in the session survey. That really, if you're hungry for more deep technical content, more broad, and more kind of things, this really lets us know the kind of things you'd be interested in. So I would appreciate, of course, a nice 5 in that as well, but also be honest with what you think. So thank you really much. I hope you enjoy the rest of your day here at reInvent. Plenty more to learn, plenty more people to connect to. I encourage you to use the hallway track as well. Sit down with somebody at lunch and find out and talk about your kind of things. Talk about serverless and enjoy the rest of your week. Thank you very much.